Hello everyone, and welcome to the first lecture video of our practical course, Cloud Systems Engineering. Overall, during this practical course, we will cover topics related to all the layers of a cloud system architecture. More specifically, we will cover the following topics. Initially, we will discuss about how to build and evaluate a single node cloud storage system. In particular, we will focus on implementing a single node key value store system end-to-end. At the next phase, we will expand the scope of this single node key value store into distributed settings, thus building a distributed key value store with multiple nodes. However, in distributed settings, the fault tolerance property is quite important. And to this end, we will see more about replication protocols, how they're implemented and how they are used. In particular, we will use the distributed key value store that we have built from the previous stage as a base, and we will employ a replication protocol, for example, Raft, for fault-tolerant cloud computing. Lastly, after having a successfully replicated distributed key value store, we are going to improve the already built system to provide support for distributed transactions. Throughout our journey, we will leverage several state-of-the-art systems and protocols such as Docker and Raft, which are actually used for building a solid cloud system stack. In this talk, we'll focus on the core components of our first goal, single node key value store. Here, you can see an abstract architecture design of the single node key value store. We have multiple clients that are connected to a server process and are exchanging data through the network. The role of the server is to process the incoming client data requests and perform the appropriate actions to store and retrieve data from a database attached to it. This presentation aims to cover all the levels of this architecture. As stated before, the clients communicate with the server through the network. Therefore, initially, we will see how it can be performed using kernel sockets. Secondly, the server is often deployed in a different host than the client. To have a consistent environment and avoid host system related issues, the server is a containerized applications. We'll see more about containers in a while. Lastly, data needs to be safely stored and retrieved from the database residing in a storage medium from the database which resides in a storage medium and all these operations have to be performed through a defined API. We choose RocksDB to be our underlying key value store. Let's not waste time and dive directly into our first topic, socket networking. When an application, in our example, the client, the server, wants to communicate with a remote one, they have to go through the whole network stack. A common high-level API that the applications use for this purpose is the Sockets API. It consists of a set of system calls that allow the setup and creation of a communication channel. More precisely, this API abstracts a communication channel and is the kernel-based TCP/IP stack interaction interface. The transmission and reception operations are transparent to the application, and the responsibilities of encapsulation and transmission over the network are being offloaded to the kernel, which directly interacts with the network card hardware. So, sockets are essentially an endpoint to achieve communication. This communication can be both between processes in a system and through the network, which is what we actually will use for building our single node key value store. Sockets support both the TCP and UDP network protocols and can work in either blocking or non-blocking mode. In blocking mode, a socket does not return control until it has sent or received some or all the data specified for the operation, while in the non-blocking mode, a socket returns whatever is in its buffer and directly moves on. Lastly, to improve scalability, sockets can be used in combination with select, poll, repoll functions to achieve I/O multiplexing. Let's have a look now on the workflow of a TCP server using sockets. The first step that the server needs to do is to create a socket. During the socket creation, the user needs to specify the communication domain, the type, and the protocol to be used for the socket. On a successful socket creation, a file descriptor for the new socket is returned. After its creation, the server has to bind this socket to an address and a specified port. As soon as it's done, the server starts listening for incoming connections. When a connection is received, the server can decide to accept this connection. Beyond this point now, the server can use the acquired socket file descriptor and send and receive messages through the established connection route. When the communication channel has to be terminated, the TCP server needs to close the socket, an action that eventually releases all the allocated resources. Note that in this slide on the right-hand side, you can see the respective API for each of the previously mentioned operations. Now, the respective flow for the TCP client is shown here. The first step that the client also needs to perform is to create the socket on its own part, on his end. As soon as it's done, the client can establish a connection to a server by specifying its address and port. When the server accepts the connection request and the connection is properly established, the client can start the message exchange with the server process through the network. When the communication channel has to be terminated, similarly to the server, the TCP client has also must also close the socket on his side and release the resources. Again, here on the right side, you can see the respective API for each of the previously mentioned client operations. Here, there is a list of references with interesting talks, documentation, and technical tutorials that can help you further with the understanding of the networking concepts. Moving on, we will get a closer look at the containers, their properties, and usage. So let's start with a brief motivation. The goal of containerization at its core is to offer a better way to create, package, and deploy software across different environments in a predictable and easy to manage way. Their usage is on an upsurge with the emergence of cloud infrastructures. These infrastructures contain a huge amount of resources. Therefore, it is quite important, both for the providers and for the users, to manage these resources in a flexible and cost-effective way. To this end, nowadays, many deployed applications are split into a fleet of microservices, and they leverage containerization for that. This methodology has multiple advantages. To begin with, as mentioned before, containers improve the hardware resource utilization as they are lightweight and the dedicated resources for each container can be predefined. Additionally, because the hosts and the platforms that run containers are generic, infrastructure management for container-based systems can be standardized and thus becomes less error-prone and less cumbersome. One more important aspect is that containers are a good fit for large and scalable systems. This is mostly due to their relatively small image size, their fast boot up times, and their debugging options. Lastly, containers can increase compatibility. For example, old applications built for older Linux versions can run on newer Linux hosts and vice versa. Even applications designed for different operating systems, for example, Windows programs, can benefit from containers and be deployed on Linux-based machines. Now, as you may know, a traditional system can be built, as you can see here on the left side. We have the user applications that run in the user space, and they are using various libraries and operating system features, and eventually the underlying system hardware. However, apart from the traditional system stack, we have the concept of virtualization. Virtualization is a process of creating, running, and managing virtual environments on computer or computing resources. It is a way of abstracting physical resources and is often used to allocate parts of resources for different purposes. The most well-known virtualization methods currently are virtual machines and containers. Virtual machines contain their own operating systems and fully virtualize the hardware and the system resources. They rely on a piece of software called hypervisor for starting, stopping, and managing the virtual machines. One important feature of virtual machines is that they offer great isolation and security. On the other hand, containers virtualize the operating system directly. They are an operating system-based virtualization technology used to package applications and their dependencies and run them in isolated environments. Due to the fact that containers do not include a separate operating system, they're more lightweight and less resource hungry compared to the virtual machines. They run as specialized processes managed by the host operating system, but they have a constrained view of the system's processes, the resources, and the rest of the environment. Containers are unaware that they exist on a shared system and operate as if they were in control of the whole host. Low-level operations such as kernel or network or I/O inside the containers are performed through the host. And also, it is worth noting that the host and each container maintain their software in separate file systems. To give you a better idea of the different characteristics of containers compared to virtual machines, let's look at some of them. Firstly, a container often encloses only a single application and packages its dependencies so that it can be functional and be deployed across different platforms. Other than this, containers also use the same operating system with the host and provide process-focused virtualization. Also, they're lightweight and easy configurable images, as well as the fast build and boot up times that they have, provide a really good balance between flexibility and speed. One further important difference between containers and virtual machines is that containers can limit access to the resources through the host operating system mechanisms, and they do not rely on hypervisors. Now, as you might know, the most widely used container engine is Docker. Docker is an application container engine. It contains a set of tools that enable users to create container images, push or pull images from external registries, and run and manage containers in many different environments. To ensure isolation between containers, Docker employs resource isolation mechanisms of the kernel. To be more precise, Docker leverages namespaces in order to limit the visible system parts from within a process. It also uses control groups or C groups to manage the assigned resources to each process. And finally, Docker makes use of the concept of layered file system to perform a file system separation between the containers themselves as well as the host system. Overall, Docker can be split into three different components. First, the set of software tools that it provides. Secondly, we have its objects that include the images, the containers, and its services. And lastly, the registry that essentially is a central repository of images. Here, you can take a taste of the whole Docker ecosystem. First of all, we have the Docker daemon, that is the software that runs the containers, pulls the images from the registry, and is a long-running process that you can always query. Then we have the Docker client that directly communicates with the Docker daemon. Here you can see also the Docker objects, as I said before, the containers and the image they have. And finally, we have the Docker registry that maintains a collection of images that one user can pull through the Docker daemon, and thus they can be used by the client. Don't forget that containers are created from container images, and container images act like templates for creating specific containers. And of course, the same image can be used to spawn any number of running containers into the host system. Now, to get some hands-on with Docker and its containers, first you have to install it. It's fairly simple in most systems. For example, in Debian-based systems, it can be performed simply with an apt install. Then you can directly run a container. Here you can see an example that provides you a shell in a container running Ubuntu. Docker provides also a quite extended set of options, such as volume mounting, setting memory limits, exposing network ports, and many others that you can look up in the Docker documentation, and you can use depending on your need. Then after successfully running a container or multiple ones, you can inspect with the Docker command line interface their state, and if they are currently running or not, if they are stopped, if they have a failure or something, using the Docker PS. And also, if you want to acquire a cell into an already running container, it can be done simply with a docker exec command with appropriate flags and arguments, as you can see here. Now, in order to create your own specialized container, first you have to create a Docker file that includes the properties you want, such as the base image, the software libraries, the software building steps that you might need to have there. Then, based on this Docker file, you can build your own image. And after its successful completion, you can run a container based on the image that you just created with the package software and its well-defined properties. Docker also provides Docker Compose in order to create, manage, and run multiple of those containers. Now, in the scenario that there exist problems with the image building, you have to know that Docker enforces an incremental build. In the case that an error is introduced in an early image building step, you might want to trigger a clean build. This can be done with the no cache option of Docker build that forces Docker to perform all building steps from scratch. Additionally, sometimes you might want to debug the applications inside the container. However, it's quite often a container to exit early when there is a failure or something like this. So you cannot actually get a cell into the debugger. To avoid to avoid this behavior, you can add the presented command here at the end of the Docker file, and thus you will be able to debug your code inside the container. And note that this was just a quick intro to Docker containers. For more information, we'll provide some useful documentation and go-to pages to learn more about containers and their usage. Now, in the last part of this presentation, we'll dig a little bit deeper into the details of our chosen key value store, the RocksDB. Let's first have a refresh of the client-server architecture we saw before. The server is usually, as we said, a long-running process that is responsible for resource management, and its purpose is to continuously receive and process the incoming requests from the client. The clients, on the other hand, are processes that send requests to be executed on the server, and after they send the request, they are usually waiting for a response from the server about the outcome of their request. Finally, we have the transport layer, namely the network, that is used to transfer the data between the server and the client. The incoming requests that deal with data are forwarded and served by the database on the server side. However, how does this system entity work behind the scenes? Let's see. When referring to databases, one could directly think of examples of relational databases like SQL. However, they're not the only way to go. One quite popular solution are the key value stores. A key value store is a data storage paradigm designed for storing, retrieving, and managing associative arrays. It can be perceived more or less as a data structure such as a dictionary or a hash table. A key value store is responsible for organizing the data and associating effectively each key with a corresponding value. It's quite important because the reason they were developed is because they are really performant, and therefore are quite widely used, as we can see right now. So the importance of key value stores can be realized if someone takes a look at the tech giants like Facebook, Twitter, LinkedIn. Key value stores such as Memcached, Redis, Voldemort are used by large companies in order to improve their data management performance and to provide faster queries response and lower latency to the end users. Apart from the industrial world, though, key value stores have attracted a lot of attention of the scientific community as well. Many research works have been published, like those presented here, that design high-performance key value stores for specialized purposes and improve their efficiency both in the algorithmic and their architectural perspective. However, designing a key value store is not a trivial process. Special consideration has to be given to its performance characteristics. A system designer has to consider the effect of log contention and how the write traffic and the memory management can affect the query operations performance. Overall, the goal of a key value store is to offer low latency operation and have high throughput, which is heavily depending on I/O. To this end, methods like operation batching can be examined and employed. Lastly, as we are talking about highly scalable systems, a key value store has to be designed in such a way to promote parallelism and efficient resource utilization, for example, in case of a multi-core instance. Apart from the performance, the offered data properties should also be well thought and predetermined. Such properties can be the persistency of the data, which means whether the data have to be stored in a storage medium or simply be kept in memory. Next, we have the data consistency model and the key value that the key value store has to respect. Finally, for the case of persistent key value stores, the crash consistency is also crucial so that the system can maintain a consistent state even in the case of an unfortunate case of an unexpected crash or an unexpected shutdown. Now, the key value stores typically support the following set of operations. The get operation, where a value is returned based on the given key. The put operation that inserts or updates a value of a key value pair. The delete operation that, as the name suggests, deletes a key value pair from the database. And range queries that apply on a range of key value pairs, depending on what the user wants to do. Here, again, you can see the client and server processes and the underlying storage on the side of the server. The server has to find a way to manage the data request from the client, as we highlighted before. For this purpose, we will use RocksDB. RocksDB is designed as an embedded library, so anyone can use it as a building block for his own application. The only required thing that we need to do is to link the server application with the RocksDB library, and of course, use the respective API. Having done that, though, the workflow of our single node key value store is as follows. Initially, the client sends a request which is received by a long-running server process. The server then decodes the message and identifies the requested data operations. After the decoding, the operation is forwarded to RocksDB, which takes care of the execution of the operations and the data placement in the storage medium according to its format. Then the RocksDB returns to the server process the outcome of the execute operation, which gets encoded into the communication message format. And finally, the server sends the encoded operation outcome back to the client to inform him about what has happened with the request operation that he had made. Now, it's time to inspect the core of RocksDB from the inside. RocksDB is based on the log structure merge tree that converts actually random writes to disks into disk-friendly sequential writes. It contains an in-memory skip list, which is called memtable. Memtable is actually a buffer that can temporarily host the incoming writes, and memtable is also normally sorted. Then it has the SS tables or sorted static tables, which maintain the data in the storage medium. They're organized in levels, and this is where RocksDB places the key values pairs persistently. The creation of an SS table depends on the memtable. To be more precise, once a map table reaches a certain size, it will be flashed to the storage, and thus it will generate an SS table. It's worth noting here that SS tables are immutable in its whole lifetime. Now, apart from these structures, and since RocksDB maintains data persistently, it has to ensure crash consistency. RocksDB therefore has the transaction log or the so-called write-ahead log, which is essentially a redo log that can help RocksDB rebuild the mem table after a crash or a shutdown. Generally, after a crash, RocksDB simply replaces the operations written in the write-ahead log and brings the system back to a consistent state. Now, when an incoming write request for a key value pair is received, the pair is first inserted into the mem table, and the operation afterwards is logged into the write-ahead log. As mentioned before, when the mem table reaches a threshold, it gets flushed to the storage. To prevent an ever-increasing SS table format, like RocksDB leverages a background thread that periodically does the compaction operation. The compaction operation essentially merges the SS tables into a bigger SS tables, into a bigger SS table, and it does that while also removing duplicate key entries, and generally does not let the SS tables expand forever. The read path is much simpler. When a read arrives, RocksDB first looks up the key in the mem table, and if it's not found, it scans the sorted SS tables to retrieve the requested value if it's actually present in the database. To summarize, RocksDB is a key value store that ensures linearizable reads, meaning that the read will always get the latest written value that corresponds to the respective key. Data durability, which is achieved through its persistent SS tables, and crash consistency by its write-ahead log. However, RocksDB does not offer replication out of the box, but provide helper functions that enable a developer to implement a replication system of his choice on top of it. When it comes to the support operations, RocksDB, of course, supports put, get, and delete operations with its API. And it also has APIs that perform the range scans, and also has support for multi-operational transactions. Now, if you want to get more familiar with RocksDB, the API, and its underlying mechanisms, these resources are worth having a look at. Overall, in this talk, we covered the fundamental concepts required to build a single node key value store, namely networking, containerization, and the actual key value store engine. Thank you very much for listening.